And also, of course, what I want to do is now go to some slides and discuss with you some what I think are very interesting aspects of the ideas of how matter and the maturity of the science and thinking about matter, how it came about. So we're going to spend the majority of the day talking about the beginnings of our understanding of just how everything around us is composed and structured and how it behaves as a result of that structure. So that's going to be the source of today. I posted some slides on Moodle under the title Lecture 2. There were a few left over at the end of Lecture 1. We did enough Lecture 1 since we missed a whole week. I don't want to belabor and talk about those things. We got more important fish to fry. So I want to move along. I'm not going to require you, there's no material on there that I'm going to be quizzing you about or asking you dirty questions about that you don't know the answers to. So don't worry about that sort of stuff because of the time we lost. Now, also, those of you that might have printed Lecture 2 out already, I was thinking about what I was going to say with regard to some of those topics earlier, and I embellished a little bit on the slides. So if you were astute and ahead of the game and printed those slides out, you might note that there might be slight difference between what you have on some of your slides and what I'm saying, but I wanted to put a little more information on some of the slides for those of you who might need a little more information. Most of the slides just might have a picture and then I discuss the ideas behind that picture. So I thought maybe a few words or 3 or 4 statements with regard to what I'm talking about might jog your memory with regard to some of the things on those slides. So I added here and there a little bit of information and even maybe added 1 or 2 slides in between for several of those situations. So what I'm going to do is I'm going to hit present now, and then I'm going to present my entire screen. And then what I'm going to do, I guess, is I'm going to hit this, and I want to share. And now I guess what I should be able to do is present my slides that I hope we can now see. And so I'm going to go to my slideshow and show these things. And the premise of Physical Science 102, the difference between Physical Science 101 and 102, and I'm aware that most of us have took 101, not all, but it doesn't really matter. These can be taken individually or separately. It's not really all that important. But generally speaking, the main topic of 101 are ideas of physics, like force and energy and things of that source, maybe a little bit about momentum and other things like that. The feature topic of the second section, 102 here, is matter and the interactions of matter and the behavior of matter. And that is the realm of what is known as chemistry. So maybe we'll just say a thing or two about what chemistry is. I have like a little definition here of what chemistry is, and then I have a cartoon here of a guy who looks very serious because he's doing something chemical. So chemistry is the science studying this composition, structure, properties, and reactions of matter. So chemistry goes hand in hand with this interpretation of matter itself. Now, believe me, it has taken centuries of development for us to get to the point where we are in our understanding of the nature of matter. Now, I should point out to you something of great interest. I think we can all appreciate the fact that humans are pretty smart. Now, I agree, we act pretty dumb. It's amazing how smart we are, but how dumb we are. And it is. It's what a dichotomy of behavior. And you think of the wonderful achievements of humans and the things that we have come up with and the technology we demonstrate, but then we can't even act civil towards one another. And it's really kind of unnerving, really, how crazy all that sort of stuff is. But in any regard, let's put all the politics and stupidity aside for a moment and just talk about what we're supposed to be talking about with regard to this. It's really fascinating to look closely at the study of our learning process, particularly from my perspective, for our learning process with regard to understanding the way the world around us works. Because you have to envision what it was like thousands of years ago when we were just simply governed by superstition or primal instincts of fear, just get out of the way of this because that's going to kill you, or let's attack this and eat it, or things of that sort. And where we have come to and the culmination of all this as to where we are now with regard to our understanding of how things work. It's quite incredible. I think you would agree with me that humans are not particularly more intelligent now than they were thousands of years ago. I don't think we have developed new uses of parts of our crania, in the past couple thousands of years. People were just as smart as we are now. We just have just such a huger base of knowledge. We have an incredible amount of information and experience of being humans available to us at this time compared to what they had thousands of years ago. What I'm getting at is that in many ways, you're a lot smarter than Isaac Newton and Galileo and some of these giants of the times, simply because of the fact that you have such a more wealth of experience and information with regard to the foundations of science than they had. Now, believe me, these guys were smart and they figured out incredibly important things. But there is much stuff about the behavior of matter that that they had no idea of, simply because of, as I said, we've been building this pyramid of knowledge for such a long time, and things that are now second nature to us were completely either not understood or not recognized or believed in during the times, even so much as 200 years ago. There was so much less base knowledge to go on. Okay, so anyways, if you were to ask me, okay, just what is a scientist? If I claim to be a scientist, what differentiates me as being a scientist compared to, a banker or something else, a cement worker or something like that? Well, if I was going to boil down the essence of what a scientist is trying to do, now this is really whether they're a biologist or whether they're a physicist or a chemist or a mathematician or any of these other so-called branches of the sciences in which we might work. I think if I was going to try to put it into a simple context of what a scientist is, I would say a scientist is a pattern recognizer. We do this scientific idea of observing what's going on around us, but then we note commonalities between the behaviors of what occurs. So I'm looking for a pattern of behavior. Then I try to fit other things to see if they fit into the pattern. So that's a vast oversimplification of what we were attempting to do. But if I was going to try to put it into one simple statement, that's what I would say, that whether you're a biologist or whether you're a physicist or whether you're a chemist like me, I'm kind of a hybrid guy. We'll maybe say a little bit about that later. But I'm looking at what goes on around me, and then I'm saying, okay, does this fit the pattern of all these things that I've observed? Now, a lot of times that's great if it fits the pattern, but a lot of times also it's great if it doesn't fit the pattern. then I have to try to modify my pattern to be able to include this new development, this new idea that I have observed as a result of the behavior. See, what we might call this is a phenomenological approach. Phenomenological means I observe it, and then I build my model upon the observation. Things have shifted somewhat in science now. A lot of people are not making the observations. They're thinking about and mathematically, abstractly applying bizarre mathematical techniques and predicting what might be happening. Then people are going to look for the predicted behavior. So there is some shift that has been occurring in this in the structure and the order in which things are done scientifically due to recent developments that have come into science in the past 100 years or so. Okay, so if I was going to like really make this guy look like a chemist, what I might do is that I might put I put some goggles on him because we want to have some modicum of safety when we're messing around with some things that might be dangerous to us. And just to accentuate the nerdness of him, I would definitely give him a pocket protector because, as we all know, there's a stigma attached to being a scientist, and there's no doubt about that. If you think in general about how society portrays people in science, they either portray them as the biggest nerd on the earth that can't walk to the door without tripping over their own feet, or they portray them in the movies as maniacal, demonic people that want to take over the world. They're evil. So either people who do science are just nerd to the max, or people who do science are just crazy. And that's an unfortunate stigma. I think it goes a long way with the fact that why we don't really have a lot of people that want to go into science. It ain't easy. I'm going to agree with that. It ain't. But I think the stigmas that are attached to being or even showing interest in it. Oh, you must be a geek, or you must be a nerd. You like science. There's a certain amount of that I think is unfortunate, because as I showed us on the first day we met, those of us that might remember that, I showed us the slide that said how many people there are in graduating from college, and what small percentage of the people that are graduating college are actually in the scientific arena and seeking jobs, to guide us in the future here. It's really kind of unfortunate. I will say this: there's lots of jobs in it. If you can manage your way through it, there will be lots that you can possibly do. Okay, so a more concise definition. Oh, I don't want to stop presenting. Unfortunately, it's on right on my slide since I'm presenting. But chemistry is the study of matter and the transformations that matter undergoes. So it kind of fits exactly with what we're supposed to be doing here in our 102. We're supposed to be studying matter, and we're supposed to be studying what happens to matter when you poke it, prod it, shoot light at it, and bounce it off each other, bounce matter off another kind of matter. Okay, so what else do we have to say here? Oh, this is kind of just showing you where chemistry and the study of matter kind of fits in the grander scheme of things. I would say that we would begin with the realm of math. Mathematics is the basis of it all. I don't know if I remember showing you the slide earlier, but I will just state I think I did talk a little bit about Pythagoras. I did. It's coming back to me. And Pythagoras said hundreds of years before the birth of Christ that all is number. And the implication is, again, as we talked about, I can mathematically model anything. I can come up with a numeric model of anything I want. So it all begins with math. And it's all about numbers. Then if I put a little circle indicating how chemistry fits into this, you will see essentially all of chemistry. I got a little corner of it hanging outside of it. That would be a corner which I maybe would call maybe the taxonomy of chemistry, just categorizing substances. You might be able to do some things like that without using numbers to do it, just based on the properties of the materials. But generally speaking, to make measurements of those properties, you're going to need numbers. But chemistry essentially is a numeric science. And now if I put some of the cousin sciences on there, you'll see there's a huge overlap between chemistry and physics. Physics is sort of the foundation. It's really not looking at bulk collections of atoms and molecules, or bulk collections of matter. Physics is looking at sort of a one entity behaving in the same way simultaneously. So what I'm getting at is, if I launch a cannonball, I'm really treating every iota of matter that makes up that cannonball as one continuous piece of matter. I don't really care about what interactions it takes between the individual atoms in the cannonball to hold the cannonball together. I'm just interested in how this collection of matter collectively has a certain mass and how it will fly through space based on the pull of gravity that it's subjected to and the initial velocity and angle at which I launched it. So we're not really so concerned about all the individual building blocks as we are about the collective behavior of the entire system. Yet there is quite a lot of, as we would say, overlap between the ideas of chemistry and the ideas of physics. Now, if I laid biology in there, you would see that there's overlap between biology and chemistry. There's overlaps between physics and biology. And there's overlaps between all three, if you like, as a matter of fact, as well. Well, if I were to put me in here, I would live in the little purple part kind of in the middle. I'm kind of like a mathematician who uses physics to study chemistry. That's kind of what I would say. And the instrument I use, when we talked about instruments, the instrument I use is a computer. I think about mathematical models that I can apply through physics to understand how matter interacts with itself and how matter interacts with any other form of matter in the form of what we call computational chemistry. So that's kind of where I live in this world. Okay, so we already did define chemistry, but what is a chemical? It's a material which is used or produced in a chemical process, we'll just say, and a substance is a chemical, of course, and it consists of one type of matter that is uniform throughout. So when I have a substance, it's uniform in its nature. All the individual building blocks that make up that matter will have a commonality to them, so that they will have similar types of behaviors, so that now collectively, as I was saying, for this iron ball, you can treat it as a single unit and really not delve into so much what's going on at the individual level, since they're all acting collectively the same. Now, of course, the reason we have to deal with substances, we can't deal with the individual entities themselves. They are, as I would say, nanoscopic. And I didn't use the word microscopic because they're thousands of powers of resolution smaller than what you can see with a microscope. Typically, you can see things through a microscope on the scale, tenths of a millimeter, hundredths of a millimeter. Anything smaller than that, you are not going to see. To see atoms individually, you're going to have to go to millionths of a millimeter, which is certainly not the resolution that you're going to be able to see through a lens type device that allows us to focus light to look at little things. As a matter of fact, I would venture to say that no one has really ever looked at individual atoms, at least in a visual sense. We have all kinds of tricks that we can use to reveal atoms, but not in the traditional sense that I can use visualization to see them. They are just literally too tiny individually for us to be able to do that. So this is one of the reasons why it took a long period of time for us to understand the nature of matter. Okay, so over the course of the rest of this period, I'm going to say many things about the history of chemistry and the history of the development of the study of matter, but you should appreciate the fact that there is absolutely no way that within the next 40 minutes, I'm going to be able to do justice to the wealth of time and effort and the mistakes and the wonderful discoveries and all the little tiny steps that were taken in order for us to get to the point where we are now so that we can understand what we now know about matter. You could not only spend a whole semester talking about those kind of things, you could spend several semesters in a course developing the history of understanding matter since the beginning of human endeavor. Okay, so again, matter is anything that has weight and takes up space. So that is what our very simple definition of matter will be. Now, in terms of our attempts to tie this in to our last unit of discussion, what we would say is we would replace two of those things that you see there with the measured quantities. So matter is anything that has weight and takes up space. We would more correctly say matter is anything that has mass, and matter is anything that has volume. Now, of course, if you're just speaking normal English, the semantics of English are that mass and volume are interchangeable. When you're making sentences, sometime in the sentence you might use mass, then later in the sentence you might use volume. But really, I scratch that. Not mass and volume are interchangeable. Mass and weight, mass and weight are interchangeable terms. But to a scientist, they really mean something very different. Weight is a force, technically. And force is something that is caused by the acceleration that a mass experiences due to a pull. And of course, the natural pull that gives you a weight, gives any mass a weight, is gravity. So weight is specific to the gravity that an object is subjected to, meaning that if I stand here in front of you in this room, I have a certain weight, but if I was on the moon, I would have a different weight. Why? Because the planet Earth pulls me differently than the satellite moon pulls me. There's simply less material there. Literally, that's the only difference. There's so much more material in our Earth, and what we can think of is just keep chopping the Earth up into smaller and smaller and smaller and smaller and smaller fragments. Every fragment of the Earth is literally pulling on me, every one of them. And if you now did the same thing, chopping up the moon, the only difference is there's less fragments. So there's less pull on the moon than there is on the Earth, simply because the moon has less mass than the Earth, period. So again, the difference between mass and weight to a scientist is that you need to talk in the context of what is doing the pulling in order to determine weight. Now, mass, though, is invariant. My mass is the same on the Earth as it is on the moon. Now, when you multiply my mass by the acceleration of gravity on the Earth, which is greater than the acceleration of gravity on the moon, then my weight is greater on the Earth than it is on the moon. Now, that's really a technical thing. I mean, does it really make all that difference? No. But it's just to make sure we're clear on the point of that's what that difference would be. And of course, mass is a measurable quantity. Volume is a measurable quantity. Okay, so those are two of the so-called properties of the matter that you're examining. So properties are a simple word to categorize what a property is that it's an observable. It's something that I can measure, and I can use that as a characteristic of the property. So with all this multitude of experience, as I talked about, we've spent so much time studying matter over the past, not just centuries, but over the past millennia. We've studied matter so extensively over that time that we now have a wealth of experience. Again, it's not that we're smarter now than we were 200 or 3,000 years ago. We just have more culminated knowledge on these things than we had in those days, so that we now have a much clearer understanding. Again, as I said, in many regards, you know way more than Newton knew about a lot of things about the behavior of the physical world, as crazy as that really sounds when you stop to think about it. Okay, so let's say a little bit about the so-called elements, and I'll have much to say about them as we go along here. A bulk sample consisting of one type of atom is what we will call an element, and I'll have something to say a little bit further on about where the origin of that name comes from, the word element. So if you have a uniform sample that at the so-called atomic level is behaving exactly the same, it only has one of these unique building blocks that makes all of the sample up. Then you have what we can now say is a visible amount of that matter that is what we will call an element. So if I have the element sulfur, in order for me to be able to deal with it, I can pour a little pile of it in my hand. Even though it is a very small pile of it, I will be holding trillions upon trillions upon trillions of individual sulfur atoms, which for the most part are all exactly the same. And it's this exact same characteristic of each of those atoms collectively that allows me to work with a visible amount of this material when I'm building new things out of that material. So an element is a pure substance only made from one kind of atom. And what we'll say is that atoms cannot be broken into simpler substances, either physically or by a chemical reaction. Okay, now, as we go along here, I don't want to belabor this yet, because we're going to spend a little more time doing it in detail. We will look very closely at the difference between physical change and chemical change. And I'm sure you've done these things in other classes, but I just want to make sure we're clear about them. So I don't want to belabor that right now until we can formalize it with some distinct definitions and examples. So all I'm going to say at this point is that when you have an element, and it's a pure element, you can't break it down into anything simpler than that pure element. You could separate it into individual atoms of that element, and each of those atoms would have exactly the same characteristics. We'll leave it at that for now, and then later we'll look at the possibility of how we might invoke those changes and how we can invoke them either physically or chemically. So for now, just for the idea of getting a definition of what's going on, we'll just leave it at that. Okay, so compounds are combinations of the elements. And of course, there are many compounds in nature as well as pure substances. I would venture to say that most of the materials that we generally work with are compounds, combinations of various atoms. As a matter of fact, anything including like this table, the plastic that makes this thing up, me and you, we of course have individual atoms in us, but those individual atoms don't exist as elements in us. Somewhat they do. Mostly they are combined heterogeneously amongst each other to form compounds. So again, we will have much more to say about combinations of atoms, why certain atoms combine in certain proportions, why certain atoms don't want to combine with others. This isn't a chemistry class, and we're not going to get crazy with these ideas. We're just going to look at the global pictures behind what motivates individual atoms. Why do they want to combine? Why wouldn't they just stay by themselves? Why wouldn't they just hang out with their cousins? And why would they want to collect together to form compounds in the first place? So we'll look at some of the motivations as to why some of these things want to happen. Okay, so now again, an idea like this, if I asked you something about this on the Moodle thing, I don't even know if I would. Why? Because I know all you have to do is turn to the slide and look this up and see what it is. So does that interest me to see that you can, oh, hello there.
Hello.
What is this? Breaking news?
No.
Breaking news. This just in.
This just in. You need to put your shield on. It's helpful instruction.
I'm okay.
That's not for you though, don't you?
I'll read it in the bathroom later. Okay, so anyways, this pie chart, I'm sure we've seen things like this before, will tell us something about what the Earth's crust is made up of. Now, first of all, what I should point out to you is the definition of the Earth's crust. It's a little different than you might think. According to a geologist, which I'm really not, but by geologists' determination, the Earth's crust does not just include the outer layer where, you know, that we can dig down with a shovel in our yard. That's not the Earth's crust. When a geologist talks about the Earth's crust, they mean the atmosphere and the dirt. So the crust of the Earth is what we exist in and around. Okay, so what this pie chart then represents is not only the dirt underneath our feet, but also the air that is attracted to this planet by the pull of gravity of this planet, as a matter of fact. And what we would find that the Earth's crust is 45.5% oxygen. Now, that shouldn't be surprising that there's a lot of oxygen in the Earth's crust, but it is not all in the air, all right? The air is only 20% oxygen. So the stuff we huff and puff on is 20% oxygen. Now, there is tons and tons and tons of oxygen in the Earth, tons of it. As a matter of fact, almost everything we dig out of the Earth is a collection of, it's a compound of elements combined with oxygen. And we have a fancy name for that. Not really fancy, but we have a name for that. We call it an ore, O-R-E. When we mine ores out of the Earth, they are elements combined with oxygen. So when we dig iron out of the Earth, we never dig out iron. We dig out iron ore, which is Fe3O4, mostly Fe3O4, but there's other forms of it too, Fe2O5, and that's what we're digging out of the Earth. When we dig aluminum out of the Earth, we don't dig elemental aluminum foil out of the Earth. We dig aluminum ore. When we dig magnesium up, we dig magnesium ore. These are all elements combined with oxygen. So there's a huge amount of oxygen in the earth as well as in the air that we breathe. So 45% of the Earth's crust is oxygen, and maybe not surprisingly, but maybe it is. The next biggest one, oh, I can't see the number underneath my little thing, but it looks like a pie chunk that's kind of almost as big as the oxygen. I'm going to guess this is around 28 or so percent. I'm sorry, I don't want to turn off the presentation. I wish that stupid thing wasn't on there. But there's a number that goes with this, and it doesn't really matter anyways. I don't want you to memorize that number anyways. Well, maybe what we would note is it's the second most abundant element in the Earth's crust. And what are the combination of these two things? Sand. Si and O make all the sand on the Earth. And believe me, there's a lot of sand on the Earth. So there's oxygen in the atmosphere, yes, and it's only 20% of the atmosphere. There's a vast majority of oxygen tied up with other elements, and most of it is with silicon on the Earth, in the Earth's crust. Then we have a smattering of aluminum. We see aluminum makes up 8% of the Earth. And then iron makes up 6% of the Earth. Then we have calcium that makes up 4.7 or about 5%, magnesium 2.8%, and then everything else makes up 5% of the Earth's crust. Now that last one should kind of be, I think you should stop and pause just to think about that as well. Because when we list at what the majority of the Earth's crust is, there's some notable things of absence there that I think are relatively surprising, like including like copper, very common materials like zinc, things we like gold. They are all lumped into the others. So that's why they are what we would consider as being precious metals. Precious metals are the ones that we have a relatively difficult time coming across. And as we move to the future, precious metals are becoming more and more and more of an issue. I promise you that. I mean, it's probably not something that you concern yourself with, but there's only a very limited amount of platinum. There's only a very limited amount of things like ytterbium and germanium. Now you might say, who cares about ytterbium and germanium? I'll tell you who cares. The semiconductor industry cares. And what do we do with semiconductors? We make all those wonderful things that makes it possible for you to hold a smartphone in your hand. And if we don't get enough of those materials, then you're going to have a hard time making smartphones. Now, this was not an issue for a couple hundred years on this planet. Why? Because the US was the big boy on the planet. We dominated everything. We took what we wanted, whether it was ours or not. That's not the case anymore. We are not the only player on the planet like we were for the past 200 years. I kind of feel bad for you guys because I benefited from the time, and certainly my parents benefited from the time when the United States was indisputably the dominant power of the planet. Things have changed dramatically, and they're going to continue to change over the next several years. China ain't kidding. India ain't kidding. And the European Union, the only reason they are a union is they realized that individually they couldn't make it. They just couldn't compete. So they had to band together to be able to compete. So when at one time we could just go in there and demand, we're taking all this, we're taking all that, that doesn't happen anymore. One of the really important commodities these days is helium, believe it or not. Stuff you make balloons out of. Yeah, but believe me, we do a lot more things with helium than just make balloons. One of the most critical things we do with them is liquefy it. And to liquefy it, it has to be really cold. And we use it as a refrigerant to power all sorts of highfalutin electronics that make the world work. And helium is becoming a really big commodity in the international scene because of its more countries want helium because more countries are running the kind of electronics and powerful magnets that you need the helium as a refrigerant for. It's becoming more and more and more a fight over these things. Whereas again, there was certainly a period of time where we dominated and we could get as much of these things as we wanted. Okay, so the point that I again will take from this is that there really ain't a lot of unique and different kinds of elements on this planet. I want you to, if you like, well, we don't have it right, many of us don't, but some of us in the room here can see the periodic table mounted on the wall. There's over 100 actual elements listed in the table, but you see the Earth is only made up of about 6 or 8 elements itself, really. Now, really, there's more than 6 or 8 because you just lump them under the all other category. But there are dominant elements certainly on the Earth, and then we scramble and scratch and scrape for all those that are in the all other category. Okay, now just another thing, just for interest, again, am I going to ask you anything with regard to these? No, because if I did, I'm used to go and Moodle and look it up and put down the number. So you could do that if I do happen to ask you something about these particular things. What are the power elements distributed in the human body? Now we see a huge amount of oxygen in the human body. 65% of the human body is oxygen, and 10% of the human body is hydrogen. Now, of course, if you add those together, you get something that we commonly hear. And what do you hear? The human body is 75% water, and that's the vast majority of what you're seeing there. This is the water. Not only, believe me, there's oxygen tied up in many other molecules in the body. There's hydrogen tied up in many other molecules in the body. But the vast majority of that hydrogen and oxygen that is in the human body is what is tied up in water in the human body. And then, maybe not surprisingly, carbon makes up the next biggest chunk of material in the human body. Now, I want you to notice that it looks like there's way more carbon than hydrogen in the human body, but you have to take into account that this is really done by mass, how much each individual atom weighs. Hydrogen atoms, as we will learn, are really light. As a matter of fact, they're 12 times lighter than carbon atoms. Or carbon atoms are 12 times heavier than hydrogen atoms. So those percentages are a little misleading in the sense that the hydrogen number looks smaller, but because of individual atoms of hydrogen being smaller, there really are more hydrogen atoms than carbon atoms in the human body. Okay, so then, maybe not surprisingly as well, the next one would be calcium, and then there's a good bit of phosphorus in the human body. This is kind of how our power systems work in the human body. And then all other elements comprise 1.2% of the mass of the human body. Okay, so what I'm now going to do is spend some time talking a little bit about the history of the study of matter. And when I do this study of the history of matter, believe me, this is going to be a very brief look at where we are and how we got to where we are compared to what we could actually spend if we really wanted to appreciate how the understanding of matter has developed. So I'm showing here a slide that begins with chemistry during the Greek period, which was, I would say, 500 years before the birth of Christ up till the time of Jesus being born. We'll say that's pretty much when the Greeks were in dominant times. Let's maybe just for a quick moment think a little bit about chemistry before that. And we'll go way back. Way back when? Well, certainly what I would first claim is there was no study of matter. We could care less about what was going on with it and how matter interacted with each other. We were more concerned about survival. So anything we gained from using chemistry was not done to appreciate or understand how the matter was reacting or acting with each other in the course of things that were occurring. We were just worried about living. So certainly the first use of chemistry by humans, I would say without question, was to gain energy, without question. We learned a long time ago that if you burned a fire, it did lots of good things for us. It kept us warm. It would light up the night. It scared away things you wanted to scare away. And you could put things in it and it would alter them. Like they probably learned early on when there was clay sitting around the area where the fire was burning, that later on that clay had changed its form. And now instead of being wet and gooey, was now hard and formed into a shape. And they probably realized, hey, I can take this mud and I can spread it out in some shape, put it by this fire, and the fire more or less dries it out. But actually, if I make it hot enough, it literally reconnects the substance making up that clay. And now I have a container that I can ornately shape any way I want by putting this material in a certain form and putting it near this fire. Not to mention that when they first started killing brontosauruses, well, there was no humans when there were brontosauruses. When they first started killing animals in the forest and just gnawing on them, then somebody figured out, hey, put that thing on the fire, tastes a lot better. That was probably one of the major advancements of the time when they learned how to cook food rather than just eat it raw. That was, I would say, I certainly prefer my food on the fire for sure. And so I'm sure that was a major, major shift in human convenience and, I don't know, whatever, just made things a lot better when they learned how to cook with fire. So fire was probably the number one early thing that humans went to for what we will call a chemical process. But I promise you, no one was concerning themselves with what is going on in this fire. What makes this fire give me all this? They didn't even have a concept of energy or what was emanating out of the fire, how the light was coming out of the fire, how the heat was coming off the fire. None of these things were of any concern. They were just concerned with what they could do with the fire. Okay, so we'll go again with millennia of time, humans just sort of meandered around using chemistry to their benefit, maybe, but not really wondering about how and what the deeper significance of the chemistry was. Until we came, we'll say, to the period of dominance of the ancient Greeks. And among them were the people I've already mentioned a few times, such as Pythagoras, I mentioned, and a few others here and there. Well, there were these two individuals that, as you can see, again, lived around 500 years before the birth of Jesus. They were Leucippus and his student, or his disciple, if you like, Democritus. And they were the first ones to come to the idea that matter was made of indivisible building blocks. We could break matter down and break it down and break it down, but eventually you got to a point where you couldn't break it down any further. So they were the first ones to propose this idea. And they even used the Greek word for indivisible. This is the Greek word for indivisible. And of course, we can now see the word that developed from their usage of the fact that I can break matter down to indivisible fragments. Well, a little later, along comes this dude. You can see it's like 100 years or so later. Along comes Aristotle. And I'm sure your mom and them know the name Aristotle. Aristotle was an incredibly important contributor to civilized existence. Aristotle was a prolific writer and teacher. He professed ideas about civics and ethics and logic, and he wrote extensively. And he was one of the individuals in certainly of his time that moved humanity forward and made it into a much more civilized existence from the chaos that had been occurring before his time. But unfortunately, Aristotle also thought he was quite the scientist. And it turns out that Aristotle was very wrong in many regards in science, not just chemistry, but also physics as well. So he published ideas about the way the world worked in both physics and chemistry, and most of them were really not very good ideas. In particular, one of the things that he's most famous for was the so-called four-element theory. Aristotle proposed there were four elements: fire, air, water, and earth. Aristotle proposed everything was made from these four elements. Everything was made from fire, air, water, or earth. And he went so far as to show you could combine some of them and get climatic conditions, meaning how the weather existed. Like, for instance, I show there air combined with fire made something hot. When you combine fire with earth, you got dry, and so forth. So Aristotle's idea was that these were the building blocks that you used, if you like. These were the four elements. Now, interestingly, he used the word element. So element is the word, as you can see on the table, we still use today. So one thing that came from Aristotle's idea was that there were building blocks, yes. Democritus and Leucippus had come up with that concept before, but his four building blocks weren't even really elements. I mean, even water is the closest to them of I guess air has some elements in it. The air is a mixture of elements, mostly nitrogen and oxygen. The air that we breathe is 78% nitrogen, 20% oxygen. That makes 98% of the air. The other 2% is water vapor, carbon dioxide, argon gas, a little radon gas, a few other pollutants that we've dumped in there as well. But that really isn't an element itself. Either water isn't an element itself. Fire is really something completely different. If you're talking, and we'll talk more about what fire really means as we go forward. It's just energy, really. And the earth is a very complex mixture of a large number of things. So none of his elements was actually an element. Now, unfortunately, Aristotle was so revered and so trusted that everyone believed the four-element theory. And I would go so far as to say for about 2,000 years, Aristotle's four-element theory remained used to describe how matter was developed and how matter existed. And it took, again, about 2,000 years for us to go away from Aristotle's idea. You can actually find textbooks published as far as the 1700s, which discuss Aristotle's four-element theory. Now, what I will also say about his four-element theory is when we use the word elements and in a completely different context, but I'm sure it sounds familiar to you. When you're out in the elements, when somebody says, "Oh, I'm out in the elements," that means it's like nasty outside. When you're out in the elements, you're out in the air and the water, and so that's the context of what you mean when you say you were out in the elements, because you're in the primal differentiation of matter that Aristotle had defined, but he did it in a broader context, that everything was made of these four things. Okay, so Aristotle came along and kind of messed things up a little bit by going way off base with what all matter was comprised of. Now we're going to jump ahead thousands of years. Why? And again, should we really do this? No, but in the interest of getting somewhere with what we're going to do, let's move to the next major period of time in which humans studied matter. And that would have been, and as I said, about roughly 2,000 years this went on. What we'll call it is the period of alchemy. And what occurred during the period of alchemy was a huge amount of superstition, of hocus pocus, of wizardry, of actually a lot of conniving and scamming and using science, or at least what we would maybe call chemistry, to fool people, amuse people, scare people, but not really study what was actually occurring, not formalizing the science and attempting to understand how the world worked. There was nothing at all in this period to do with any of that. Think about if you were in the 1300s or whatever, the 1200s, and there was all these little kingdoms and fiefdoms with a bunch of people living in just horrible conditions, but you had some tricks up your sleeve. You were able to take this magic concoction of a few powders, put them together and put a spark on it, and then it would make a big puff of smoke and a little bang, and you'd say, "Huzzah!" or something like that. People would go, "Ooh." So you could use tricks like this to entertain people, to scare people, to dupe people, to gain advantage. And so a period of time like this, chemistry was kind of shrouded in mystery and complete misunderstanding, superstition, and there was really no advancement going on at all. No one really cared to understand what was happening, but people would just use techniques of chemistry to their own advantage. There was lots of work on the transmutation of lead during this period. Now, what I mean by that is that if you took a chunk of lead in one hand and a chunk of gold in the other hand, you would notice striking similarities. They both are very dense, meaning a little pile of either of them has a lot of weight to it. If you put equal piles of, say, aluminum in this hand and maybe iron in this hand, you'd say, yeah, they're just not as heavy. But lead and gold had these characteristics of a certain sample of them had the same kind of like oomph to it. Another thing was that lead and gold were both malleable, meaning you could take them and very easily work them. Get a little hammer, start pounding it out. You could make all kinds of interesting shapes out of the materials. And of course, with gold, that led to it, not only because it was pretty and all that, but it led to make all kinds of ornate things out of it, of course. But so since these physical properties of gold and lead were so similar, people said, well, there must be some simple way in which I can change one of these into the other. So when I say that there was a large time when transmutating lead to gold was important, I'm not kidding. A lot of people invested a lot of time. A lot of people duped a lot of other people with the attempt to change lead into gold. And so there was lots of underhandedness rather than really formal study of chemistry during this lengthy period of time. Now, believe me, if somebody really wanted to today, I think they could make lead into gold, but the cost of making the lead into gold would be so astronomical that it certainly wouldn't be worth making the lead into gold. Maybe someday it would be, but right now, currently, that would just not be economically feasible to do so. So during these periods of time, this chemistry was kept cryptic, meaning, let's say I know a little trick how I can take a pile of mixtures of these things and make it go woof, make a flash, make a sound, and scare a bunch of people or entertain a bunch of people. You think I'm going to show everybody how to do that? No, I'm going to keep it a secret. I'm not going to share my idea with the rest of the world. I'm going to use this for my own benefit and gain. So there was no sharing of information, no transfer of knowledge that would further the ideas of science. So chemistry in this period was used for individual gain and was not collectively, in a communal sense, used to advance the science at all. Okay, so then along comes this guy. You will notice this is early on compared. Oh, let me back up just one thing. You back up and you see that up until about 1650, I'm calling that the alchemy period. Alchemy is a word which means it's kind of chemistry, but it's kind of hocus pocus. And think about it, as a matter of fact, before I go any further, that's what chemistry is. When I see a flash, when I hear a sound, when I see a color change, I don't see the individual atoms doing the magic that makes that flash, sound, or color change. I just see, it looks like magic. It looks like it just occurred with no other impetus than I was able to hocus pocus conjure it. So it's easy to understand why there was some mysticism to the processes of chemistry that were being employed. But notice this ranges in the Western Europe up until the 1600s, where this guy who lived in the Middle Eastern area, who lived, as you can see, in the years around 770 AD, where he lived, he was now actually doing formal science study. He's the first person that I recognize to really think about what was going on. So this is the first individual who studied things, thought about why they were happening, and tried to figure out how they were happening. He did lots of studies in math. He also just did lots of little chemical experiments and wrote down his findings as to the behavior of matter. And he wrote the earliest known textbook that has survived that really now could be used as a basis of knowledge. So he gathered the first basis of knowledge of chemistry, if you like. Now, his name was Jabir Afla, whatever, however you say that, I'm not really going to try. But what they did in the Western society was changed it to Geber because it sounded, when they would talk about his work, they wanted to make it sound Western, I guess. So they gave it that name in Western use of his studies. Now, it's interesting, his name was Al-Jabir or something like that, and that's where the word algebra comes from. So he did the mathematical basis of algebra, and it comes from his name. And another use of his name in English is the word gibberish, because he was also famous for making all kinds of puzzles and riddles. And so when he would present puzzles and riddles, they called that gibberish. Okay, now, interestingly then, what was happening in Western Europe and all that, where so-called civilization was still the alchemy period. There was still the period of transmutation of lead into gold, of people traveling from kingdom to fiefdom and doing little wizardry shows and not sharing their information and things of that sort, until along comes this guy. You can see now we're getting up to and around, the Revolutionary War in the United States. So this guy is Antoine Léon Lavoisier. And Lavoisier is revered as the father of modern chemistry. And the reason he's the father of modern chemistry is that he wrote the definitive textbook that was translated from French into English and French into German, spread around Europe, used it. There were plenty of universities. Harvard was open by this time. University of Georgia, believe it or not, was open by this time. So this was a commonly used textbook where we were now formalizing science. We were now studying and thinking systematically using the so-called scientific method to understand how matter worked. So finally, we're maturing to the point where we're not treating science, or in particular chemistry, as magic, as something to fear, as something that can't be understood or figured out. It just happens. We were now being able to formalize it into a mature science. Very important, as they say, paradigm shift in the way we treat our understanding and development of education in a particular arena. Okay, now having said that, let me tell you the real story. Here's the real story of Lavoisier. Lavoisier was a rich dude, and you can kind of tell that just by looking at him. That ain't the way normal people looked back in the day. Lavoisier had a position of power and influence in France. Lavoisier was an educated person, and so was his wife. And it turns out his wife, whose name was Marie, because every woman in France in the 1700s was named Marie, but not only that, Marie was very educated too. And she was educated in Arabic languages. And Marie got a copy of Jabir's book. And Marie said, wow, this is pretty cool. Now, don't get me wrong, Lavoisier was a smart guy, and he was in a position of power, so he had leisure time. Where most people had to work for a living, he could sit around his estate and think, he's bored and think about things to do. So they got a copy of this book, and Lavoisier said, well, let's try some of these things out. And he said, hey, that's pretty cool. So Lavoisier learned about science through Jabir's book, and then it was translated to him by his wife. So then Lavoisier essentially took the stuff out of the book and made his own book. So I kind of little. So that's the story of where Lavoisier, and he's now, like I said, revered as the father of modern chemists, but he kind of stole it from Jabir. Now, here's the moral to the story, though. I don't know if you're a buff of history, but you might know the date he died was 1794. I don't know if you know what was going on in France in 1794, but what it was the French Revolution. And what happened in the French Revolution was that all the important, rich, royal dignitaries were being guillotined. And Lavoisier was, among other things, a powerful land-owning person of leisure who was a tax collector, had an area where he collected the taxes from the people and all this kind of stuff like that to support him and his wife's rock and roll lifestyle, which culminated in something good. I mean, he brought this book to Western society, but Lavoisier and his wife were guillotined in 1794 during the French Revolution. Okay, so I guess what we'll do is we'll stop there. Look, again, I'm about finished with my stuff. I promise it's going to be posted today. And then I'm going to give us a week or so. It'll be open for us to play with. I will send an announcement when it's posted. But when it is, go out there and see what you can do with it. And then we're just going to continue with this lecture next time. See you next week. Peace out.